more one-sided limit problems. The first one is a piecewise function f of x equals to 2x if x is less than or equal to 0 equals to x to the third if x is greater than 0. So we have x approaches to 0 from the left and from the right. So when x approaches to 0 from the left, so x approaches to 0 from the left, so that means we are looking for a number that is slightly less than 0, which is negative, right? So that means we are picking the first piece. So that will be a 2x. So this one, you take a 2 times that number. That is fine. You don't need to show any table value. Just 2 times a number that is very, very close to 0. So as a result, you can think about 2 times negative 0.00000001. So the result is getting very close to 0. So this one you can just say y approaches to 0. And then on the right hand side, x approaches to 0 from the right. So think about a number that is slightly greater than 0, which is positive. So we have to plug that in to x to the third. So you take that positive number, you raise that to the third power. So just think about this 0.001. You raise that to the third power. So the result is very close to 0. So in the previous problem, think about 2 times negative 0 point and then a bunch of 0 and then a 1. So as a result, that is very close to 0. So this one, you take that raised to the third power. So this is equals to 0. This is the left limit and then this is the right limit and they are equal, right? So they are equal. So what does that mean? That means we can draw a conclusion. Limit as x approaches to 0 from either side of f of x. The answer is just equals to 0. What if they are not equal? The left side and the right side, they don't have the same result. If they do not have the same result, then we say limit as x approaches to 0, this number just does not exist, right? Because you have a point right here, right? In order for the limit to exist, it can be either solid or empty. You have a curve approaching to the point from the left side, and then you have a curve approaching to the point from the right hand side. They must meet at the same spot. So that's why the left limit and the right limit must be equal. Okay, so take a look at the yellow one. So we have a quadratic divided by linear. So limit as x approaches to negative 3 from the right. X squared plus x minus 6 divided by x plus 3. So negative 3 plus 3 in the denominator, that gives me a 0. So that is a problem. I cannot just plug in right now. Let's see if the top can be factored. So if you look carefully, the top can be factored. So you can factor that to x plus 3 times x minus 2. So 3 times negative 2 is negative 6, and then 3 plus negative 2 is 1. Okay, so divided by x minus 3, and then you can get rid of the x plus 3, right? So now our biggest enemy is gone. When you plug in negative 3, you are no longer having a 0. So the result is negative 3 minus 2. So that is equals to negative 5. That is the answer. And then what can we say about the negative 3? So x equals to negative 3 is a removable discontinuity, because we can do some algebra to get rid of it. So what's the graph look like? You see that the rational function has an x squared, right? So most people might be thinking, all right, the graph is just some sort of parabola, right? The answer is that is not right. So when you graph this, you are actually graphing y equals to, or I should say f of x equals to x minus 2. But we started at x squared. They don't look the same. No, think about this. You can get rid of the x plus 3. So when you do the graph, you are actually graphing x minus 2, even though you just do some table value. So the math you are actually doing is x minus 2, which is linear. The slope is equals to 1. The y-intercept is at 0, negative 2. So then where is the removable discontinuity? It looks like x equals to negative 3 is a vertical asymptote. So no, there is no vertical asymptote in this case. So when you do the graph, so let me just give you the graph. This is the x-axis, and then you have your y-axis. This is y and this is x. So when x, we definitely have a y-intercept at negative 2, right? So at negative 2, there is a y-intercept and then the slope is just equals to 1. So you are supposed to have a line that looks like this. What happened when x equals to -3? So when x is equals to -3, we have -3 minus 2 that equals to -5. That means -3 comma -5 is an open circle. -3, -5, that means I have to erase this point and then change that to an open circle. The open circle represents a removable discontinuity. What if the x plus 3 cannot be removed? Then that is a vertical asymptote for non-removable discontinuity, which is the next case. So do you see that there is a blue limit? So let's copy this blue limit and then bring it down. So we are going to copy and then we bring it down. So this one, as x approaches to 2 from the left, I don't really care left or right. When x is equals to 2, we have a 0 in the denominator. So this one I cannot just plug in. Can we do any simplification? The answer is no. 2 plus x and 2 minus x. Okay, here. You cannot get rid of the x, right? You cannot cancel the 2, you cannot cancel the x because we have a plus, we have a minus. They are not multiplication, so nothing can be cancelled. Then what can we do? Let's take a look at the table values, shall we? So first of all, I'm going to pick some x value and then I will show you the f of x. Okay, so we are approaching to 2 from the left. That means the number must be a little bit less than 2, but it's getting so close to 2. How about this? We pick 1.9 that is close to 2, closer, and then even closer. And then you can just plug it into x. So the result is 39, 399, 3,999. So as x approaches to 2 from the left, y approaches to really big, right? Which is positive infinity. So the result is equals to positive infinity. And then when the result is equals to positive infinity, we call this DNE, does not exist. What is the graph look like? Without drawing the graph, do you see that on top you just have a 2 plus 2? So the top is just a real number, right? You have a 2 and then you add some values to it. Okay, it's just a number or a real number. What happens if you take this minus 2, I should say 2 minus this, very close to 2. What happened? So we get a number that is very close to 0. Another way to say this is the difference between these two numbers is very tiny, which is very close to 0. And so you have a real number divided by a number that is very close to 0. Like you have, let's say 4 divided by this. This is very close to 0, right? What is that equal to? This will just give you a positive infinity. You can try this on your calculator. That will just give you a huge number, which is positive infinity. That is another way to think about this limit. So I already showed 2 ways. A picture, not a picture, a table value, and then you can think about this real number divided by something very close to 0. Another way to think about this is you can sketch a graph, but if you don't know how to sketch the graph of this function, that is fine. Maybe calculator is not allowed during the exam or quizzes. So let me show you the graph anyway. So the graph is, this is my x-axis and then this is my y-axis. And then we have x cannot be equal to 2, right? Because we don't want a 0. So that means when x is equals to 2, we have a vertical asymptote. So when x is equals to 2, we have a vertical asymptote. As x approaches to 2 from the left, y goes to positive infinity, and then when x is equals to 0, y is equals to 1, right? So the graph will just look like this. If you check out the graphs, I should go this way. If you check out the graph, there is a horizontal asymptote, but don't worry about it. The graph looks like this. If I change the problem to x approaches to 2 from the right, then your answer is the limit or the y approaches to negative infinity. As a result, the limit does not exist. Okay, so that is the end of this video. If you think my instruction is clear and helpful, give me a like, share the video for me. Click the subscribe button on your way out. I appreciate for your help and support. See you all in the next one. Signing out.